Iron is one of the most important engineering materials. However, it exists in various intermediate forms such as bloom iron, sponge iron, and pig iron, which are produced during the manufacturing of steel, cast iron, and other alloys. In this video, we will clearly explain these three forms in a straightforward and exam-friendly way. Welcome to the channel. Iron is one of the most abundant rock-forming elements, making up about 5% of the Earth's crust. It ranks second in abundance among metals, following aluminium, and is the fourth most abundant element overall, behind oxygen, silicon, and aluminium. It is a dark, silver-gray metal that is highly reactive and oxidizes easily. In nature, iron is rarely found in its pure form within rocks. Instead, it is usually combined with oxygen to form iron oxides such as hematite, magnetite, goethite, and limonite. Primary minerals used as ore for iron production are hematite and magnetite. The processing of hematite and magnetite ore involves crushing, screening, and grinding to produce both hematite lumps and fines. Magnetite ore undergoes additional processing through magnetic separation, which is a crucial step in producing magnetite iron concentrate. Now that we've gotten background information on iron, let's take a closer look at the three intermediate forms of iron that are produced during the production of various iron alloys. 1. Bloom iron. Iron blooms are intermediate products created by melting iron ore in a bloomery. In ancient times, the smelting process involved forming a bed of red-hot charcoal in a furnace, to which iron ore mixed with additional charcoal was added. This type of furnace operates at lower temperatures but still effectively separates metallic iron from unwanted elements. The furnace works by reducing iron oxide-rich ore using carbon monoxide, which is generated from the incomplete combustion of charcoal. Typically made of clay and stone, these furnaces were designed to be heat-resistant and operated manually with bellows. The hot carbon monoxide from the charcoal reacts with the iron oxide, stripping it of oxygen and forming metallic iron and carbon dioxide. Other undesirable compounds in the ore, such as silicates, have lower melting points and liquefy within the furnace, allowing them to be removed as molten slag. However, primitive furnaces could not reach the melting temperature of iron, so the metallic iron pieces gradually settled at the bottom of the furnace and sintered together into a large spongy mass filled with slag. This barely usable product is known as a bloom, which is where the name bloomery originates. While the bloom is still hot, the iron is worked and refined through hand forging, which helps draw out the slag and produces wrought iron. This iron bar, wrought iron, can then be used to make tools and weapons in a standard forge. Bloomeries are no longer used for industrial production. They have been replaced by more efficient blast furnaces. Mechanical properties of bloom iron. Research has shown that bloom iron tends to be brittle in its raw form due to the presence of slag, which results in low ductility and toughness. However, through extensive forging, bloom iron can achieve high strength, comparable to that of hardened steel. The hammering process expels the slag, enhancing the density, ductility, and overall toughness of the material. 2. Sponge iron. Sponge iron, also known as direct reduced iron, is a highly versatile and essential material in the steel industry. It is produced by directly reducing iron ore, in various forms such as lumps, pellets, or fines, to metallic iron, using a reducing gas or elemental carbon derived from natural gas or coal. The aim of this process is to remove oxygen from all forms of iron ore without melting it, which means that the process temperature must remain below the iron melting point of 1538 degrees Celsius. As the oxygen is removed, micropores form in the ore body, giving it a porous texture. When examined under a microscope, the final product has a honeycomb structure, which is how it earned the name sponge iron. Unlike pig iron, which is produced in a blast, sponge iron is created at relatively lower temperatures, typically between 800 degrees Celsius and 1200 degrees Celsius. There are various methods for producing sponge iron, with the most common being the coal-based rotary kiln process and the gas-based reduction process. Each method has its own advantages and is selected based on factors such as raw material availability, energy sources, and environmental considerations. Coal-based rotary kiln process. In this process, iron ore, in the form of lumps or pellets, is mixed with non-coking coal and fed into a rotary kiln. The kiln is inclined and rotates slowly, allowing the iron ore to flow down its length while being heated to temperatures around 1000 degrees Celsius to 1100 degrees Celsius. As the iron ore travels through the kiln, it undergoes a chemical reaction with the carbon from the coal, which reduces iron oxide to metallic iron. The resulting reduced iron, or sponge iron, is then discharged from the kiln and cooled. This process is widely used in countries with abundant coal resources, as it offers a cost-effective way to produce sponge iron. Gas-based reduction process. The gas-based reduction process uses natural gas as a reducing agent. In this process, iron ore, either in the form of pellets or lumps, is fed into a shaft furnace and heated to temperatures between 800 degrees Celsius and 1000 degrees Celsius. Natural gas is reformed to create a mixture of hydrogen and carbon monoxide. This gas mixture reacts with the iron ore to remove oxygen, resulting in the production of sponge iron. The reduced iron is then discharged from the furnace and allowed to cool. This gas-based reduction process is known for its high efficiency and low environmental impact, as it produces significantly lower carbon dioxide emissions compared to coal-based processes. Sponge iron is distinct for its high metallic iron content and consistent chemical and physical characteristics, providing secondary steelmakers with flexibility in preparing furnace charges. This flexibility allows them to produce finer quality steel than what can be achieved using steel scrap alone. 3. Pig iron. Pig iron is an intermediate product obtained by smelting iron ore with a high carbon fuel such as coke, often combined with limestone as a flux. It contains a high carbon content, typically ranging from 3.5% to 4.5%, along with various impurities including manganese, silicon, sulfur, and phosphorus, which make it very brittle. Due to these characteristics, pig iron has limited direct applications. Primarily, pig iron serves as the foundational feedstock for steel making and other iron-based alloys. The production process involves adding coke, iron ore, and limestone to the top of a blast furnace or smelting furnace. Hot air is injected from the bottom to ignite the coke. As the material descends, the coke reduces the iron ore to molten iron, while the limestone reacts with impurities to form slag, which floats on top of the molten metal. The heavier pig iron collects at the bottom of the furnace and is then discharged. The term pig iron derives from the traditional method of manufacturing, which involved using molds to create a branching structure in sand, resulting in multiple individual ingots shaped at right angles to a central channel, resembling a litter of piglets suckling from a sow. Once the metal cooled and solidified, the smaller ingots, the pigs, were easily broken off from the thinner runner, the sow, hence the name pig iron. In conclusion, pig iron, bloom iron, and sponge iron are all products derived from iron ore, but they differ in their production methods and physical properties. Pig iron has a high carbon content, typically ranging from 3.5% to 4.5%, along with silica and other impurities. As a result, it is brittle and not suitable for most direct applications. Sponge iron, in contrast, is known for its high metallic iron content and consistent chemical and physical characteristics, offering steelmakers flexibility in preparing furnace charges. Bloom iron is also brittle in its raw form due to the presence of slag, which leads to low ductility and toughness. However, with extensive forging, it can achieve high strength comparable to that of hardened steel. From ancient bloomeries to modern steel plants, each type of iron plays a unique and crucial role in metallurgy, impacting our daily lives in multiple ways. If you found this information helpful, please like this video, share it with your friends, and subscribe and turn on the notification bell for more engineering and metallurgical content. Thank you for watching, and see you in the next video.